There we go. All right. So yeah, I appreciate all the hard work you guys are doing all semester. And I know that's less than optimal. That said, let's get to some problems and see if we can learn something here. So this live stream is going to be very similar to the one I did earlier. So if you already watched it earlier, it's not going to be that much different. Just because I picked out a couple of problems I thought were pretty good. And we're going to start right here at 5.31. I believe this is on page 92. 92. Okay. So let me get this down here. Let's go here with this annotation. All right. So let's read through this together. You have a block of mass M, hangs on a massless, inextensible string. When you see, let's start with the inextensible. When you see inextensible string, what does that tell you? Do you remember?
Okay, so that means the acceleration has to be the same?
Yeah,
right?
So I'll call this A3 should equal A1. Now in this case, I'm just calling this one object 3 because its mass is 3m, and this one object 1 because its mass is 1m. Nice job. What does the massless mean?
Constant.
A is constant. Excellent. And these are our default assumptions. So every string is going to be assumed to be massless and inextensible unless otherwise specified. And then what is the phrase that helps us identify tension 1 equals tension 3? How do we know the two tensions are equal?
Negligible axial friction.
And
the mass of the pulleys.
Mass.
Yeah.
Oh, is that negligible mass of the axle?
Yeah.
Okay.
The pulley of negligible mass. And so it's the combination of not only of negligible axial friction, but also negligible pulley mass. So that's what allows us to say T3 equals T1. Outstanding. That's cool. Now, those are our standard assumptions unless you hear otherwise. So on your test, you know that's the standard assumption, even if it's not written. Okay. Great. Okay. So the second mass is partially supported by an inclined plane. Got it. The angle theta can be adjusted by a local zombie. Great. And then it says, at what angle will the two blocks be in equilibrium? What does equilibrium mean?
Like entirely balanced, so it's not like nothing is.
Excellent. I would say forces balance. If the forces are balanced, that tells us one other thing. What is the acceleration if forces balance?
0.
A equals 0. So this is a fancy way of just saying A equals 0. So it's saying at what angle will the two blocks have A equals 0? That's what this question is asking. Now, when you see this, obviously it's a chapter 5 problem, but when you see this kind of stuff, hopefully you get the idea, maybe we should do a force problem, which means maybe I should, what do we start every force problem with?
An FBD.
FBD. Now, how many blocks do we have in this problem?
2.
So how many FBDs do you think we need?
3.
2.
You could do 3 if you wanted to, but you only need 2. So there, what was the third one you were thinking of, Esteban?
The system where the tension is the internal force.
Exactly. So now I just want to point out Esteban's doing this in his brain. He's saying, I could say there's a coordinate system this way where this is X, this is Y, and that the acceleration is 0. And he's saying you could do a system FBD. That's absolutely right. However, the total number of FBDs required to get enough equations to solve this system is 2. If you have 2 blocks, you need to do 2 of them. So to Esteban's point, he could do the system and then either one of the 2 blocks by themselves. Or I think it was Jake said, why don't I just do the 2 blocks by themselves? And to be honest, I would probably do the 2 blocks by themselves as well here, just because we want the practice. And when you have to start drawing coordinate systems that get all bent around, that's a sign to me of like, you know what, I'm just going to do each block separately so I don't screw up. It's not that you couldn't do the system though. Esteban, is that clear?
Yeah, I was thinking more of a doing the 2 FBDs of each block and then adding them together.
That's exactly right.
To get the third, the system, just to get a full pair. Yeah, I wouldn't do the bent coordinate system because I'm not comfortable with that yet.
Exactly. And I'm not either. And I've been doing it for a long time. So I don't expect you to ever get comfortable with it. There's certain cases when that's good. So let's go ahead. You guys go ahead and draw what you think, and then I'll draw what I think. Okay. So I'm going to draw on the board as well, and then we'll compare. Do you guys like that, or would you rather I just draw it live right in front of you?
Yeah, I like drawing it on my own and see if I got it right or not.
Okay, yeah, it's just kind of like try to make it slightly more game-like. So, okay, so give it a shot. I'll draw mine, you draw yours. I'll put the thing back up on the screen so you don't have to look for it. Okay, so that's what we're doing. So try and draw an FBD of 3M on the left. And this is question 5.31. I got an idea. Okay. So I drew my free body diagrams. I made one mistake on purpose. Tell me what it is. It's subtle.
You forgot the 3 on the 3M.
Yeah, this was mass 3M in the problem. So this should be 3mg. Nice catch. All right. And so now typically we're going to set up our coordinate systems. Now, I don't know if you recall, but there was this sort of went up this way. Then it went around here. So what I would recommend is, why don't we call this direction the X direction? Generally speaking, that works pretty well for inclines. So we're going to call X direction parallel to the plane. And then over here, notice this way, if I rotate this around, I notice that down is actually the X direction and to the right is the Y direction. You don't have to do this. Any coordinate system should give you a correct answer. However, I think you're going to like this. So that's why I do it this way. I'm going to turn on another light here just in case. I don't know if that helps see better or not. I don't know if that did anything or not, but whatever. Okay. So now, any questions about this from anybody? You can speak up at any time. What was the acceleration in this problem? I usually like to put that in here. Wasn't it 0, I think?
Yeah.
All right, thanks. Okay, so which one of these force vectors do I need to split up?
The gravity.
Yep. Okay, so I'm going to split it up. Tell me what I do wrong. I'm going to deliberately make a mistake. I got my right angle. This one looks like let's see, it's adjacent. What am I doing wrong?
That's the hypotenuse right there. So
exactly. This doesn't make sense, does it? It's right here. This is wrong. Your components, okay, two things. You could tell you screwed up right here. Number one, the hypotenuse should always be longer than either of the components. In that case, this one was longer than that. That's clearly wrong. The other one is the x-axis is parallel to the x component. So if I look here, it should be this way. And that's the right angle. And notice the magnitude of the vector should be opposite the right angle, which now, which of these angles is theta? The upper one or the lower one?
The upper.
Let's check. This is my trick to remember. So Esteban claims this is theta. Let's see if that's true. Well, in this picture, I know that this is theta down here, right? Well, if that's a right angle, that makes this 90 minus theta, which that leaves theta for right here. Now, I have a link. So if you're having trouble seeing these angles, just give me a sec. Whoops. The other day, whoops, where's my Zoom? The other day I made a quick practice video. It's only like 5 minutes long. But so that video that I just gave you in the chat should help you kind of practice the angles I just went through. It's only 5 minutes long. So you can check that after class if you don't understand this. And I could help you in office hours after class too. But for right now, I want to move on. Here's my trick for remembering this. 1, draw MG straight down every time. 2, draw a fake little inclined plane here. Use that to do the geometry to get theta. Usually theta is the angle up here, but not always. What if I had called this angle theta? Well, then this would be 90 minus. So sometimes it's theta, sometimes it's 90 minus. It could be a different one like phi or alpha or beta, whatever. After you get that done, get rid of this junk because it doesn't belong on your FBD. So you could do that trick, basically draw the inclined plane and use that to figure out the angle, then erase it from the FBD. That's my trick for you. All right, so that means this side is going to be what?
Cosine.
Okay, so what's the whole component?
3m.
Good. I was just
theta.
making sure you remembered that. One of the common things students forget is they keep forgetting the 3, but Esteban's all over it. Nice job. And then while not always true, usually the component perpendicular to the plane has a cosine in it. The component parallel to the plane usually has a sine in it. Nice. Let's write some x equations, y equations. Go ahead. You write the x equations and y equations, and I'll do it as well. And maybe what I could do is just kind of raise this up. You can't see me writing. So it'll be like a little game here. So go ahead and see what you think.
A is 0 in both directions, right?
Absolutely. It's an equilibrium. Okay. It's an equilibrium in all directions.
Right.
Nice job.
Okay.
Good job. Okay. I'll give you about 10 more seconds, and I'll show you what I got. It's okay if you're a little slower than me. I have been doing this forever. I'll do one more drink of coffee. There we go. Hopefully that's what you thought.
I wrote it a little differently, but yeah, same idea.
Yeah, so go ahead, Jake. Tell me how you wrote it differently.
So I got x is 3 mg sine theta plus tension equals 0. Which I believe
you mean negative 3 mg plus t? So we got to be careful here. Yeah, so this is, okay, so this is where we want to focus. Let me say something here really quick. On this particular problem, you could be pretty loosey-goosey. Anytime a equals 0, it's kind of like, yeah, whatever. But if for later problems, when a is not equal to 0, it's super important that you make sure the components match the coordinates. Look at this one. This one is going down. This one is going down the plane. So notice.
Oh, I had that going the other way. Okay. For some reason.
Remember, this is another trick. You could tell if your two components have the right direction by saying, look, I know I need to get from this point to here, right? And so from tail to tip, the arrows of the components need to take you to the same position. If you had drawn it going this way, you'd be going down, then up. That would put you over here. That's not correct. Does that make sense why I'm going down and then down?
Yeah. Yeah. I for some reason in my head, I was like thinking that was the tension force, but it was gravity. So
it relates to it because you could tell that this has to equal that in magnitude, right? So that's why I'm saying it's kind of like you could get away with a lot of mistakes in this simple one. We're trying to learn it for the, So you may have actually gotten that problem fully correct with your technique. But in general, this is going to get it right even when A is not 0. That's why I'm trying to focus that way. Good. All right. A lot of you probably just wrote number 0 here too, right? So there's no reason, but I did want to focus on, don't forget, you can't just write M times 0. It'd be 3M. Again, for this particular problem, not a big deal, but what if A was some number? If you forgot that number 3, everything's going to be wrong and you'll do all this work for nothing. So remember, use the correct mass times A. Other thoughts on this one? What was I doing here?
You saw that A was 0, so you just added the negative 3mg cosine theta.
Actually, it's basically what you said mathematically, but this was the reason in my mind. If acceleration is 0 up and down, all the arrows up equal all the arrows down. And that to me is a faster way to do it. So it's saying the ups equal the downs, which is the same thing he said is, I think what Jake was saying is, couldn't you just say this? And then add 3mg whatever to the other? Yes, they're the same thing. Nice job. All right, so there's a couple of different ways to see this one. How about over here? Why is mg the positive term here for me?
Because the coordinate system is flipped.
Yes, so if I follow that... Oh, yeah. We'll let Esteban get the next one. Okay, got it? And then from here, we're supposed to get what? So here's a big reminder. After you get FBDs and force equations, reread the problem because it's been so long. What are we supposed to be getting here? Let's go take a look.
The theta.
What angle? Got it. Theta. Okay, so how will we do that, Esteban? What do you think?
Well, I was thinking you would probably solve for tension first. So I was thinking
which equation?
I would probably use the second block.
So solve for T.
Solve for T, and then plug it into there, and then.
So let's see. Do you agree? Hold on. Let's just catch up. T equals mg. So what Esteban's saying is, can't you just replace this with mg? What drops out, Esteban? Remember, this is all equal to 0. What does every term have in common?
Mg.
Yeah, so we can cancel out the m and the g. So you get a 1 here. You get sine inverse of 1/3 if you do the math. Cool. That's how and so we see there's a variation on this one. Now we know what angle to put the ramp if we want to balance this thing. Great. Why is that useful? Well, maybe we want to get the angle to be approximately that, so we don't need to apply a ton of force to get this thing to move, right?
Wait, so can't you factor out mg, right? Oh, and then you divide it so it becomes...
Yeah, so...
Okay.
You could go through the solutions later. I'll just pop them up here. I think they're here. The idea is you could do this, right? And so I'm more interested in practicing the setups. So let's get to the next one. Is that cool?
Yeah, I see that now. Okay.
Yep. So yeah, I'm going to kind of gloss over the solutions and focus on the. So remember, in these types of problems, when you see this stuff, if I put a problem on a test like this, I would probably give maybe, let's see, 2 points for this FBD, 1 point for this FBD, 2 points for these force equations, 1 point for this force equation, and then maybe 3 points for the answer. So notice here, and maybe I'd even make this worth 2. I don't know. But so you could see that most of the points actually come from setting these things up. The rest is just algebra, checking the units, etc. Okay. Let's go on to the next one. I'm going to give you a second to look at this one. Just letting you digest for a minute before I ask you a bunch of questions, okay? Okay, you got 4 blocks, 3 strings. Unless otherwise specified, all of our strings are ideal strings, massless, inextensible. All of our pulleys, we're going to assume our pulleys are ideal pulleys for right now, okay? So if you were going to, okay, and then it says at some point in question, a determined acceleration magnitude, blah, 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 blah. Assume the rightmost mass actually travels to the right. Okay, got it. Friction is negligible, understood. Okay, so I don't know, any thoughts, anybody? Where would you start? What are you thinking?
Draw all the FBDs.
Okay, how many do you think we need?
4.
Probably need 4, and why not just do 1 for each block? So in each FBD, what's something you need to specify in the FBDs so you could write force equations?
Like subscripts?
Yeah, or coordinate systems, right?
Okay.
So yeah, which that will give you your subscripts, etc. Or oh, I see. You were thinking of mass 1, mass 2, mass 3, etc. Yes, absolutely. That's absolutely true as well. I guess I was thinking of one of the pieces of my FBD is I always have a coordinate system. So pick a block and tell me the coordinate system you want to use for that block.
I would start with the 4th block.
4th block right here. Which way do you want the coordinate system to be?
I would go positive X in the right direction and then Y up.
Normal.
Mm-hmm.
Normal, right? Okay. Mm-hmm. And then which way is this thing going to accelerate if you had to guess?
Well, it says it accelerates to the right. It moves to the right.
It says it travels to the right, so I'm going to assume it accelerates to the right. That could be a mistake, but we would just get a negative answer then, so that's fine. Okay, so Esteban, based on that, what do you think I would want you to do for block 3?
You would have a coordinate system parallel to the ramp.
Okay, like this?
No.
Aha, like what?
So you would keep the L the same, just slant it.
Yeah, so the trick, so to communicate, I'm trying to focus on this. This would be called down the plane. So if that helps you guys communicate with each other, say X is down the plane and Y is perpendicular to the plane. And I think that's what you meant, right, Esteban?
Yeah.
So those are the words that are going to help you communicate with each other. Just say down the plane if you need to do that. How about block 2?
Same as block 4.
Yep.
And then block 1 would be same again.
Ah, so you're saying do this? Aha. You could do that. You could do that. However, what do you think I would do?
Y go to the left and X going up.
Like that, right? X and Y. Now, you don't have to do this, but this is what I recommend. And I recommend it for reasons we'll see when we finish this problem. Okay, so take a look at that one. Got this thing cruising. That is what I chose to do for my coordinate systems in the solutions. So before you get all crazy, what about the strings? Do they all have the same tension?
It doesn't say tension,
Yes.
actually. Does it?
Well, let me ask you this. There's this tension right here. There's also a tension on block 3. Are those going to be the same? If you had to assume.
I would assume yes.
Yes. How about this tension? Would that be the same?
I would assume the tension's the same on all the string.
That would be wrong. So different strings can have different tension. So just give me a second here. So you guys know the directions of the accelerations and the coordinate systems. Let's go back up to here. In this previous problem, the tension was the same because there was only one string. However, take a look at this one. If you have 3 different strings, you're going to get 3 different tensions. Now the tension 2 is the same here and here. Tension 3 is the same here and here. But the idea is if you have a different string, you should expect different tensions. Does that make sense? Why these no longer have, so you would have this tension, and I think in the solutions I drew that in red. And then the next one, I think I did it in green. And the next one in blue, I think. So the idea is there's 3 different tensions you would use. I think I called this T1, tension 2, and tension 3. So if the pulleys have negligible mass and negligible action friction, the tension is the same throughout that one string. But if you have more than one string, okay, all bets are off. Is that clear why they're different, Esteban?
Yeah, I'm trying to picture myself drawing the FBDs because I'm thinking, so there's a tension 3 between 4 and 3, and then so there's an action reaction to that for. So I guess I would have to
I tell you
draw them
what.
out so I can.
Yeah. So what I was going to suggest right now is I'm going to just wait a minute and let you try and draw them and think for a minute. And I'm just normally we go to a breakout room, but I'm the only one here, and it's a small group, so we're in a breakout room now. All right, so I'm just going to shut up and stay out of your way. You guys take a minute to digest this, and then I'll come back and bother you in a few minutes here. So take 2 minutes to just kind of get a start and get your brain wrapped around it. Try to do it without looking at the solutions and see how far you get, and then we'll talk about the solutions together. All right, take a few minutes. I'll give you another about 45 seconds, okay? And then we'll start talking. Okay, so I'm not sure if you had enough time. Do you guys need another minute or two, or do you want to start maybe looking at what I had and compare? It's up to you.
Can I have just like 1 minute?
Yeah, one more
Yeah,
minute.
yeah,
One more
just-
minute. Yep. Okay.
Just trying to do FBDs.
Yeah. And if you've already done that, you could start working on the force equations or whatever. I'll give you all another minute and a half. So, right, the main thing here is, can you get FBDs and force equations? That's the bulk of the point. So, yeah, FBD is the hard part. If you screw up that, everything else sucks. Oops. All right, so let's go ahead and take a look. Hopefully you had a minute there. I'm going to start by showing the solutions, and let's look at the FBDs, okay? There are other correct ways to do this, but these are the FBDs that I chose to draw. Notice the coordinate systems pretty much matched what we were talking about. So let me see if there are any questions about any parts of this one. I guess something I could do here to mention this angle in here is probably theta. And this angle right, oh, go ahead.
Yeah, I overthought FBD3. I like broke T3 and N3 into components, but I realized you don't have to do that because of the coordinate system being tilted like that.
Absolutely. And so we see now why we end up rotating it, right? So you're like, all this time until now, it's never really been that obvious, but I'll just show you something here. Whoops. And then the acceleration is off this way, right? So here's the deal. There's no reason you could do this coordinate system right here. But if you do that, how many vectors do you need to split up?
3.
4.
Oh.
You also have to do,
Oh.
you see where I'm going with this? Look how crappy it is to not rotate your coordinate system. So once the problems start to get significant, we see that, oh my gosh, this one, this one, this one, and this one, none of those 4 vectors needs to be split up. By rotating it, we really only have to split up 1 vector instead of 4. That's so much better than this up here, in my opinion. And that's what I don't know if you noticed, but that's what all these boring words are for. Blah, 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 blah. So that's why you come to class. So you don't have to read so much boring stuff. All right. Is that good?
Yeah, makes sense.
Sneaky, right? But it's like hugely advantageous. Let me get rid of all these drawings on here. Other questions? Anybody?
I'm kind of confused on the how the M3G cosine and M3G sine.
Yeah. So remember, if I could, whoops, let me hold on a sec. Got to do things in just the right order in Zoom. Hold on. I'm going to point out, do you remember that down here, this was theta in the picture, I think. Can you confirm that for me, Kev?
Yes.
Okay, cool. So do you agree that this is my trick? That's a right angle. What's this angle here where I drew 2 dots?
Some theta minus sine, 90.
90 minus theta.
Yeah. Sorry.
Yep. And so then what's left for this angle right here where I'm drawing 3 dots?
That would be theta.
Is that what you needed?
Yeah. That's
All
that,
right.
you know.
Yeah, so notice what's sneaky here. I'll just point something out. In the previous problem, notice the angle was going the other way, and this thing right in here, right where that blue box is, was theta on that one. So for this one, down here is theta, which makes this 90 minus theta, which leaves this is theta. So another way you could do this is the skinny triangle trick. Notice theta is the angle that's much less than 45. Clearly, that's much less than 45. If I go to my next problem, I could see that down here, my angle theta is clearly much less than 45. This angle right here is also much less than 45. Right? Is that good, Kev? Another way to see it?
Yeah.
Right on. All right.
I have a question. Why do you have a force on the FBD 4?
Oh, in the problem that was just said some zombies pulling on it. This capital F.
Oh, okay. Yeah. Thank you.
Take a look at the problem statement. You'll see that they said, "Oh, suppose the zombies pulling on it," and it was just some random thing I threw in there. Otherwise, think about this. If you didn't pull on this, there's no reason to expect these to necessarily go to the right. In fact, they might go to the left because this hanging block might pull it downwards. And in fact, it should. So without the zombie pulling it to the right, we would actually expect this whole system to be pulled by this mass over here, M1, and it would all go to the left. Which we actually already solved that problem. Because if all you have to do is do this problem and set F equal to 0, you could actually set F equal to 0 after the fact. You would get a negative number for A, which implies a negative number to the right. That's the same thing as a positive number to the left. So all these would go that way. Is that good, Karen?
Yeah, thank you.
Right on. Okay, let's take a look at the force equations. Nothing too crazy. The hard part's getting that FBD right. If you screw that up, you're toast. Now look at this. Now we will see the advantages of lining the coordinate systems with them always in the x-axis. Look at this. If I stack the x equations, I made a typo here. This should say right side, but whatever. So just kind of looking at these problems right here. If you look at this, Notice if you stack them and add them, the red internal force drops out. The blue internal force drops out. And the green one also drops out. And you're left with these two forces are positive. This one's negative. On the other side, what do you get? They all have an A, so you could factor out the A and you get mass total. Now, I forgot to actually solve this for the acceleration. If I wanted to get the acceleration, I'd have to divide both sides by m total. So A, and I just forgot to do that last step. So I need to fix that up. So it'd be a bunch of crap over m total. I think you could figure that out from this line. That's not too bad. But I'll fix that up tonight. Okay. Any questions about that? Any of this before we move on?
So in the third FBD, or rather in the third force equations in the y direction, because of the flipped coordinate system, it's not accelerating in the y.
Correct. And so that's a huge advantage. Notice by rotating that coordinate system, one of your force equations is easy. The other one sucks. Don't get me wrong. It sucks, but it's so much better to have one suck and one be easy in general. Yeah. It's easier to solve for stuff. Other questions? Let's go look at that problem again. So we pretty much did all of that. And then notice in part B, it says the masses are identical. Well, that means you could just change M1, M2, M3, and M4 just to M. And then you could solve this for F. Okay, so at this point, the rest of it's not too bad. I'm going to let you do the rest of that one at home. The point of that problem was to show you, oh my gosh, if you get used to doing this trick where you follow the coordinate system around with the string, I think you will find you can always stack the equations and add them, and then you get the system FBD without having to draw the system FBD, which is what Esteban was alluding to earlier, which is a good point. Oh, sorry, yawn. All right. Let's go back and let's look at another one. Question 5.34. This one right here is a great problem for practicing your angles, because you could see one of them, it has it parallel to the plane, and one of them has it horizontal. And so this is a great problem for practicing the FBDs and seeing how they change. So if you need more practice with angles, this might be a good one to do after class. 5.35. This is a good one to do as a review problem before your final exam. It's got a VT plot and it's got FBDs. So this is a good one to kind of see how forces and plots relate. So I'm going to leave that. Okay. I guess I was thinking of Tower of Terror. Ooh. Okay. Here's another one with some angles, action, reaction, pairs, blah, blah, blah. Oh, here we go. 538. Let's do this one next. So I'm going to give you a second to read here. I'll give you a minute to kind of read this one, and then I'll talk to you in a second. Okay. So in this case, obviously we're in chapter 5. Obviously this is a force problem. However, what are some clues? Maybe you'd see the word tension. You know, tension is a force. That's a sign you might want to do. Or even this one, normal force. So if you didn't see this right away on a test day, because on test day, all the problems get mixed up, but you'd look at this problem and see, I got some blocks. It's talking about forces. Maybe, just maybe, I should figure out some force stuff. So when you see that, what's the first thing you're going to do when you see this type of problem?
FBDs.
How many do you need?
3. Yeah.
3.
I'd
That
say
was
maybe.
Karen. Oh, go ahead. What were you thinking, Jake?
Oh yeah. I was gonna say maybe a system between 2 and 3 as well. So 4. But
So 3, and then the fourth would be optional. That's exactly how I would view it as well. We know you need 3, so you could always do 1, 2, and 3. However, it might be nice to do a 2-3 system on this one. So it might save some effort if you did that. What is the advantage of doing a 2-3 system FBD?
get rid of some internal forces.
What is the internal force?
That would be like the action reaction pair between 2 pushing on 3 and 3 pushing on 2.
Exactly. What type of force do you think I would call that in the solutions?
Normal.
Right. It eliminates normal force 2, 3. So that would be, and notice, look at the questions we are asked. Part B says get N2, 3. So this system FBD, while not required, may actually make it easier to get part 1, right? So I'm going to write something down and I want you to tell me what's wrong with this. I'm going to start drawing the FBD for object 1, okay? FBD, I'll just say M1, okay? I know that there's tension up. There's only one string in this problem. I know there's M1G, which I guess if you wanted to, you could just call it MG, because it says in this problem, M1 is M. So in this case, I would say that T equals MG because the ups equal the downs. And then we could go on and do the next FBD. So tell me what I did wrong. And there was something wrong here. Something horribly wrong.
Is it there's like a different, no, I was going to say different tension, but there's not.
Yep, I'm just listening.
Is it because of the coordinate system?
What about it? That's
I'm trying to think. Because I was originally trying to figure out which way I was going to put the coordinate system. I was going to, so if it's accelerating.
How about I just say this? I'll just put my coordinate system like this. That's legal, right? Any coordinate system is legal. You could also do it like this. You could also do it like this. All of those are equal. Heck, we could do it like this. Any one of those coordinate systems would work. So it turns out drawing the coordinate system doesn't matter that much. Something huge is wrong here.
Signs?
Nope.
Acceleration is not 0.
There it is. Isn't this thing going to accelerate?
Oh, shoot.
Yeah, this is huge. The only time T equals mg is when acceleration is 0. Now, how do you know it's going to accelerate? If friction is negligible, There's no friction here. Isn't this thing definitely going to slide down? If there's no friction, it's going to slide. So what is the correct force equation?
T minus mg equals ma. Well,
Nope.
Yeah, ma. No.
So okay, so he's saying T minus mg equals ma. Now I just want to point out, look at this.
Negative ma.
That would be correct. The other way you could write it is mg minus t equals ma. But the point is, we do know that these two need to have the same sign. So remember when we started this chapter a couple of weeks ago, that was the very first problem we did. And it seems like so long. And what I found is students still screw up this FBD when I put it on the final. It's crazy. It's because we get so used to problems where A equals 0 and it doesn't matter. But every once in a while, A is non-zero, and then it's hugely important. We saw that this was the most common mistakes are saying this or saying this up here with the, right? People say this all the time. Both of those are wrong. Now, let me point something out. Everybody makes mistakes. You are going to make mistakes too. However, the advantage of doing the rotated coordinate system that I suggested to you where is it? Oh, come on. There we go. I knew it was in here somewhere. Take a look at this one. This is the way I've been recommending to you, like this, and then follow it, right? If you do that, you have a way to check your work that we didn't have before. So it's not that the way I'm telling you is the right way or even the best way, but look, when you get these force equations, now you know, okay, if they're all accelerating in that kind of curvy path, I know that I should get total mass times A, so yeah, basically you could do that. I don't know. Is that making some sense, people? Or do you have questions about this while it's up on the screen?
Yeah, and that's what I was trying to picture in my head is that rotating coordinate system.
Yeah.
Yeah, and so because mg is going in the same way as acceleration, that's going to be positive. So you're minus the tension force of the string. So that all makes sense.
This balances that. This balances that. And so basically, this is the force that causes the system to accelerate. Tension is internal, so we don't worry about that. Normal force between them is internal, and you get this. So this is actually the fastest way to solve it. However, just like Esteban was saying, geez, this is a lot to kind of visualize in your mind. I do not recommend doing the system FBD. So I would do kind of like Karen said, just do this, boom, boom, boom. Make sure you use the rotated coordinate system like this. And then just the problem works itself out after you get that. Yeah. What do you think, Esteban? What do you think of the system FBD now that you see it?
That makes sense.
Okay. Other questions? I'm just letting you soak it in for a sec. All right. And so I think that's plenty of good practice. Obviously, you've got a quiz on Wednesday at the start of class. So I think you guys are getting pretty good at this, but just do a couple more practice problems and you should be good to go. Physics is always sneaky. There's always something, but hopefully it'll be all not too bad. Hopefully you like this more than you like the projectiles and stuff. And hopefully there's no typos. Actually, you guys probably are hoping for typos, right? So that you could retake the quiz, but yeah, we'll see. Let's see. What did I want to? Oh, I know what I want to do next. So, okay, so that's pretty much it for our force and free body diagram practice problems. Now I want to show you a simulation just to finish the day and kind of play with it a little bit right with you guys here. I think it's this one. All right. So here you could see I have an inclined plane. And right now I'm going to point out a couple of things up here. I could toggle the friction on or off up here in this by saying ice. You could have no friction, or wood, there'd be friction. I could show the sum of forces right here by clicking this button. Notice, because you don't see any arrows, the net force is equal to 0 right now, okay? And you could change the angle and some other stuff here. All right. So the idea here is, let's go down to 0. Let's try this. Whoops. Let's start out with the flat. Okay. So in this case, let's put this on one. Okay. So now I have this ready. The idea here is, if I start pushing on this thing with 100 newtons, notice if I pause this, right now, this normal force, sorry, that color is bad. Oops. Right now, this normal force and the force due to gravity balance because we're on a level surface. So notice the force applied is actually equal to the sum. Because these two cancel, there's only one force left. All right, let's clear this out and just watch it. Okay, so I'm going to run this one. So in this case, it may be difficult to tell because we're doing this over the internet, but I do want to point out the object is not moving with constant speed. So watch it, and hopefully you agree with me when I hit play. I'm going to hit play in a minute. When I hit play, try to watch the speed of the object and agree that it's accelerating to the right. We see it gets faster. Okay, that's great. So now watch what happens if we put an incline here. And what I'm going to do is I'm going to apply a force of, how about 300 newtons? And let's start this thing at, whoops. Let me start this thing at, oh, let's just play it, whatever. Okay, so let's just let this run for a minute. And when you watch this thing, we see, watch the sum of forces. On the flat surface, the applied force is bigger, is big enough to keep it accelerating to the right. But when you're on the incline, it's not. So what's the story here? Let me pause it. And actually, I'm going to jack this up to something really big. Now, and let's play this. All right, so when it goes up there, what I want to point out is, look at the gravitational force. Watch this one. In particular, I want you to observe if the gravitational force changes. Okay, here we go. I'm going to play it. Just watch the gravitational force. Also watch the normal force. Here it comes. I hope you agree the gravitational force is not changing. Well, that makes sense. This is just mg, straight down. That's always the gravitational force. What is changing, there's a component perpendicular to the plane and a component parallel to the plane. Now look at these two forces here. Look at this applied force versus this component down the plane. At this moment, which direction should this thing be accelerating? Up the plane or down the plane, based on what you see?
Down, because the perpendicular force is larger.
Yeah, so we see that this component right here that I'm drawing red lines on should be bigger than this component right here. As a result, the acceleration should be down the plane. That's why we see the sum of forces is down the plane. The net force, or F sum, is equivalent to the acceleration times the mass, and it goes down the plane. So let's run this thing again for a second. Right now, I want to point out what direction is the acceleration. We said down this way. What direction is it moving?
Down that way, down the
So
incline.
should it be speeding up or slowing down?
I hate these kind of questions.
They point the
I think it's
same way.
Speeding up.
Speeding up. Excellent. Okay. Yeah. And so I'm trying to kind of synthesize it. So all the stuff that we've been talking about relate. Isn't this, it's like a blissful torture. Okay. So now watch. It's speeding up. Now I'm going to play this. Now look at this. In this case, look what's different now. It's accelerating this way. Which way is it moving?
Still backwards. So it's slowing down.
Yes. So now let's watch and see if it slows down. Now, at this moment, all of a sudden the velocity is this way. It's speeding back up. Then when it hits the incline, it'll be moving this way, but acceleration will be this way, and it'll slow down. And so, okay, just kind of keep the velocity of acceleration and watch this as it goes. V up the plane, A down the plane, V down the plane. Oh my gosh, this is crazy, right? All right. So hopefully this is making some sense why it's making this operation. Any questions about this while that's running?
So I don't know. This might be kind of unrelated, maybe office hours, but so say before like he even wanted to push the thing and say he wanted to make it go over the ramp. He could just like draw an FBD of the thing on the ramp and he knows the angle. So he can figure out what force he needs to apply to like surmount that gravitational pull to like push it right over, right?
Whoops.
Does that even make sense?
I think so. Say what you said again. He could do an FBD on the plane, figure out what force it should be. Yeah. So tell me, what force should it be? This is a crate. It's got 100 kilograms. The angle is 49.2 degrees. How hard should you push? Remember, when you go on the incline, isn't this usually theta? And what is this component here?
Right.
mg what?
Sine theta.
So punch that in your calculator really quick and tell me a number. While you're doing that, I'll put this thing, now it's on pause right now.
Okay. 742 newtons.
There we go. So right now.
Oh, that just cancels it out. Okay.
Exactly. So if I do 741, which way should it creep?
It'll start going back down.
Okay, so let's make this a little more dramatic. How about, right? Whereas if I make it 750, it should start.
And it's going to start creeping up and over.
Yep. Oh, better make it.
Okay, that's cool.
So if I make it 790, what should happen? Oh, no. All right. So that's cool. So that's kind of our frictionless case. Now I want to show you why this gets nasty when you include friction. So chapter 6 is all the same stuff. However, we're going to add in friction. So for the next 8 minutes, I'm going to show you what happens, why we need a whole chapter just for friction. So let's take a look at this case. In this case, let's start with 100 newtons. Notice the following. It's active, right? I hit the play button. It's not going anywhere. To prove that to you, I could do 1,000. And there it goes, right? But so in this case, let's start here with 100. It's not going anywhere. 200, not going anywhere. 300, it's not going anywhere. And notice what's happening right here. The force applied right now is 300 newtons. And notice the force due to friction. If it's not going anywhere, what number does that have to be?
Negative 300 newtons.
Okay, or 300 newtons is the magnitude, and this is the minus sign. Are you okay with the arrowhead being the minus sign?
Yeah, yeah.
Cool. Okay. All right. And so as I increase these numbers, we see that this just keeps stepping up. Now, let me see. So even all the way up to, I think we could even go up to 489. So in this case, I just want to point this out. Right now, this is 489 newtons. And this one over here, the applied force is also 489. Now I want you to watch carefully what happens. I'm just going to increase the force by 2 newtons, okay? Or actually, let's just take this up to 500, okay? Now when I hit enter, let's see what happens. Watch the frictional force carefully. Did you see that? What happened to the frictional force?
It went from bigger to smaller.
Yeah, estimate how big it is. If this one's 500 newtons, what do you think the frictional force is if you had to estimate?
Well,
just kind of eyeball it.
270.
All right, I'd go with that. That seems almost perfect, actually. All right, so what we see here is there's 2 types of friction. There's static friction. Notice down here at the bottom, there's a coefficient that says static friction. The static friction is related to half the weight. And then the kinetic friction is going to be basically 1/3 of the weight in this special case. Now watch what happens here. I'm going to start this again, except I'm going to take this up to 1,000. Now when I hit this, all I want you to do is focus on the size of the friction. What if I do 2,000? Notice the size of the friction is not changing once you get it moving. However, all right, what? Oh, okay, there's more here. Oh my gosh, this is crazy. Look at this. Let's get this over here. Okay, so now if I have 0 newtons, there's 0 friction. If I have 100 newtons, I get 100 newtons of friction, 300, etc., all the way up to about 490. Okay, so at this moment, once you go past that, anything over that, oh, it must be 495 maybe. Still not moving. I think it was 500. There we go. Oh, I forgot to hit play. Sorry. There we go. So anything over 490 causes this thing to move. And once it's moving, the friction drops to a different value. And at that point, no matter how much force you apply, we see the friction doesn't change. So this is very complicated. All right, now watch this. What if I set this force to 0? Watch when I hit play. What happens to the net force? Oh my gosh. In this case, I just want to point something out. This thing has a net force this direction, so the acceleration is to the left. However, it's moving to the right. Notice friction does not oppose the acceleration. Friction causes the acceleration. Friction opposes motion. It does not oppose acceleration. And what we have seen is acceleration and motion are not synonymous with each other. Velocity and motion, those things have the same direction. All right. Now imagine, okay, so I'm going to pause. Any questions on that? Now what? Yeah, it's so we're going to do all the. You can see. Look at this one now. Let's say I put a. Let's say I do 600 newtons here, and let me actually look at this one. This is crazy. Let's do 0. Friction can be up the plane, down the plane. All right. So watch what I'm going to do now. I'm going to apply 600 newtons. And I want you to watch what happens to this carefully, everybody. Watch. So let's try this. Here we go. It's enough to make it move. Now it gets on the ramp. And now I have not hit the pause button. Okay. Just to be clear, I'm not hitting the pause button. So in this case, look at this complicated problem. We start out with your accelerating this way, friction's this way. So that's how this problem started. Then we went to friction this way. The normal force changed, the frictional force changed, and you're actually accelerating this way. Finally, I don't know if you could tell this, but this frictional force is a very small value, close to 0. And what's the acceleration in the final state? 0. I hope you agree that this looks somewhat complicated when almost identical problems have wildly different values. You apply the same force under different situations, you get wildly different results. If you apply the same force on a horizontal surface, it accelerates. If you apply it and it's already moving, it's going to be moving but slowing down. And if you start it from rest, it's not going to move at all, and there's almost no friction, even though friction is present, and that tiny bit of friction matter. Oh my gosh. Moral of the story is we need to spend some time working on this. That's why friction gets its own chapter, chapter 6, pretty much. We're going to pick that up next time. It's time to go. Any questions?